Hey guys, it's Michael with Breaking Concepts. So right now we're going to continue forward with our discrete logistical growth model. And in part one, we have already taken a look at kind of what it is, some of the definition, some of the logic behind all of this, and basic concepts. So here we still have the logistic growth model, discrete one. So today we're going to talk about the logical explanation. So let's actually start by multiplying the equation. So from here to here, we'll get something like nt plus 1 is going to be equals to nt plus nt r times 1 minus nt over k. And actually, what we can see is we can see an nt plus 1 is going to be equals to this one is our current population. And here's a guess. What do you think this chunk of meat is? Well, in fact, actually, this chunk of meat is going to be equals to the net change of the population. This is going to be our birth minus the death. So this actually kind of resembles the definition of a recursive sequence, right? Nt plus 1 is equals to our current population plus this chunk of thing. And this chunk of thing you can actually think about as a difference equation of nt. So that's how we can think about it, right? Our current population in addition to the change. And the change could be the net change of population, birth minus death, okay? And so you might be wondering, like, how is this resemble of the net change of population? We have literally 1, 2, 3 terms within this product. So let me just take out this and write again. So the net change, right, is going to be equals to our nt times r times 1 minus nt over k. This is the net change. And so this is the net change. It doesn't really make sense sometimes because if you remember from our previous equation, we've shown that nt plus 1 is actually equals to our nt plus our inflow population, which is beta times nt, and minus our mu times nt, which is our outflow population. This here should be a addition and subtraction, right? And this one, the net change this time, is a full product. Well, so here's the entire explanation of the actual net change. And we can kind of rearrange some variables as we go. So first of all, the average net change, right? The average net change is equals to the ideal growth rate, right? We've talked about this is the maximum potential when, the resources are unlimited and the population is super small. And I've already explained why that's the case in our first video. So if you forgot it, feel free to check it out, our part 1 series. So this is our ideal growth rates, right? The R, right? And we want to multiply by the available resource. And within these two, what do you think is the available resource? Well, the available resource is going to be 1 minus nt over k, right? And then we're going to times the current population size. So here's exactly what's happening here, right? So let's have a thought experience. Let's look at just the ideal growth rate multiplied by the available resource. So the ideal growth rate basically is saying when there's unlimited resource, right? The maximum capacity. What is the maximum rate of growth? So writing on our fish example, let's say our ideal growth rate is 4 fish, right, per person. That's the ideal growth rate. That's the maximum. And let's say, the available resource is basically 100%, right? 100%, there's absolutely no limitation with what you can achieve. So 100% is basically here. When it's 100%, we should have 1 minus 0 because 1 is basically 100%. And the only time that we can make it 0 is when nt is equals to 0. So 4 fish per person times 100%, basically you're saying that, okay, we can grow at the maximum rate. Let's say right now the population has already taken a lot of space and we're more close to the carrying capacity. Let's say we have already taken 90% of the capacity. When we've taken 90% of the capacity, what that means is nt over k is going to be equals to 0.9, right? 90%, right? What happens is you have to sub this into this equation. So you'll get 1 minus 0.9 and then you'll get 0.1. So after having 0.1, then you multiply this by 4 fish per person. Basically, we know that when we're already at 90% of our capacity, the growth rate would not be 4 anymore. It will not be our ideal, but instead it will be the 10% of our ideal growth rate, which is 10% times 4 fish per person. This would be the growth rate when we are already at 90% of our capacity. Okay, this one, let me highlight that again. This is the total growth rate, right? The actual growth rate when we're already at 90% of our capacity. And I hope that makes sense. We have, for example, this whole thing, all we gotta do is to multiply the entire growth rate by our current population. So logically, this is what is happening and why this is the net change. And now you might be asking, a net change should have positive, right, the positive difference, as well as negative difference, right? When the birth minus the death is higher, there should be a negative net change. And how do we show that? So imagine this scenario, right, where we're just starting out. When we're just starting out, the population is very small, and NT is basically close to 0, is basically approaching 0. So we can remember our formula where we have R times 1 minus our NT over K and multiplied by our population NT. Let's take away NT for now. Let's look at the inside here. When NT is approaching 0, let's say NT is 0. Let's take a limit. If NT is really 0, then we can find out that, it's going to be 0.0 over K, 1 minus all that. We've seen this from our last video, so the rate is going to be R, right, times our NT. It's true that we can sub NT is 0, but this is not what we're looking for. What we're looking for is when NT is similar, is close to 0, right there. Let's use our previous example where the carrying capacity is 1 million, and currently maybe we have five fish, something like that kind of ratio. Right? So we can kind of see that, okay, so during that time, the total growth rate should be around R. And then multiply this R by our current population. 5 times R of fish is going to be produced for our next generation. It's going to be born and added into our next population. So let's say R is again 4 fish per 4 extra fish per person. Then you'll get 5 times 4, 20. So there's 20 more fish going to be added into our population. All in our NT plus 1, it is going to look something like 5 plus 20. Remember, 20 is our, the birth, the one that we gave birth, right? So we have 25 fish in total. The scenario 2, when we're at maximum capacity. When we're at maximum capacity, we would have NT is going to be equals to K. So when NT is equals to K, we have R 1 minus NT over K, and then times NT. So we have this again. So what we get right now is R is going to times 0 times NT, and therefore the entire thing is just going to be 0. Remember that our equation is basically NT plus 1, right, equals to NT plus our difference equation, right? This is the entire thing that we see here is basically our difference equation, right? So given that, we basically know that at maximum capacity is basically NT plus 1 equals to NT plus 0. So it's just NT plus 1 equals to NT. And again, this is the concept of equilibrium that I've mentioned from last time. The next generations forever moving forward is just going to be the same as NT. So before moving to the next scenario, I really want to highlight again, the reason why I had 0 for NT here, but not for this one, is just because I want to show when NT is approximately close to 0. And the fraction itself could actually be 0 even though NT is still very, 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 very minute, like 5. Okay, it's just an approximation over here. Right? So fraction-wise, it's going to be equal to 0, but NT itself is not 0. It's close to 0, but it's very small. So imagine something like this, right? You have something like 1 over 1 million, right? Something like this. Then it's basically just 0.0000001, something like that, right? That is the reason why I'm taking this as 0. The fraction itself at 0, and made it here for 0. but NT itself, it is not 0. It's just 5 fish here. So here's scenario 3, when the population overshoots. Population overshoots, what do you think is going to happen? Well, there's too much fish, right? There's too many fish, right? Or whatever. Then population is going to start dying because we can't handle that much. Be it through, fighting, right? Lack of resource, starvation, whatever. So again, using our net change, we're going to see R is going to be multiplied by 1 minus NT over K, and then multiplied by NT. So because we know that NT is greater than K in this case, this side is going to be negative. We're going to have a negative. So all in all, in general, because R is positive, NT is positive, right? The entire change, right? This is basically our GNT, is going to be negative. And remember from our equation, we have NT plus 1 equals to NT and plus our GNT. This is positive, right? But this is negative. So this time, we're going to have a future population that is smaller than our NT, which means you're going to look at something like this. NT is going to be greater than our NT plus 1. So this is why this part of our equation is simply equals to the actual net change. Now the reason why we have a 1 here, again, is just to factor in the current population. Remember from our original video, from our part 1 video, I've mentioned something about non-overlapping generations. The same thing here. That was the formula that I used for non-overlapping generations. And actually, we have a discrete logistical growth model for non-overlapping generations, and it will be this one. And so the one that we're actually using is this one, and this one actually is for overlapping generations, which means if the old generation survives alongside the new generation, then we will get something like this. There's actually 3 types of model for logistic growth model in general. The logistic map is actually the same as logistic at the previous discrete growth model, but what the X means is instead of having actual populations, for example, instead of having actual populations, we would have fractions of population over its maximum capacity. So what this unlocks, the logistic map, is that it unlocks something called dimensionless. Basically, you're saying that we don't have to factor in units, we don't have to factor in anything. We're just showing that the relationship of this logistic growth model. And we need to understand for both of these models, they are chaotic. And the reason why I'm saying is chaotic is, I'm going to give you an example. Let's say we have a population maximum of 4, right? Within our tank, like let's say it's 4, and suddenly we're going to add maybe 50 fish into the tank. So what do you think is going to happen if I add this instantaneously? The maximum of 4, and we add 50 fish. T plus 1, we would have 0 fish left. 0 fish left, or maybe 1 or 2. And the reason for the drop is because in nature, think about it. If you have a maximum of only 4 and you have 50 fish inside, what's going to happen is they're going to be overcrowding, they're going to be fighting for resource, and most importantly, they will produce so much waste that is very detrimental to any fish. So the entire population can easily down to 0 or to only 1 or 2. And that's why it's called chaotic. It's chaotic because it is unpredictable. Continuous logistic growth model is is totally different. We had previously what we call a difference equation. Now here we have a differential equation. Okay, this is differential equation. A differential equation basically is saying that it is a continuous equation. And if you guys study calculus, and remember in calculus, we kind of talked about the only solution for this differential equation, dp over dt equals to rp, is exponential functions. That's why when we model population growth, right, we will have something like this. Because in population, the rate of change of population is proportional to the amount of population right now. Now, the only difference that we have here is that we add this term, 1 minus p over k. And this term is very similar to what we have been seeing, is the 1 minus p over k is the same as 1 minus nt over k. So this p here means population. This is saying that when the population hits, right, our p, it's equals to our k, the capacity, the rate of change would be 0, right? 1 minus 1 minus 1, 1 minus k over k is 1 minus 1. 1 minus 1 is 0. 0 times all this, and dp over dt is equal to 0. There will be no change of growth. And the graph would actually look something like this. Here, we start with an exponential curve, and then it will, kind of levels out over here at k. But in a nutshell, this is the continuous logistic growth model. So I hope that makes sense, and I appreciate everybody for staying in here. Thank you so much.